it doesn't pass through the body. So that's the Meissner effect. It was discovered by these guys that as superconducting states, bodies repel every other magnetic field that comes in contact with them. And these are the very huge application in transportation, things like the maglev train and all that. I'll come to that later. But then that's pretty much the long and short of it. Then the second one is the zero resistance to currents. So that's like a summary of what superconductivity is about. It means that there's zero resistance, and that means current can flow for as long as possible. Some guys conducted an experiment and they were able to sustain the current consistently for about 2 years. Like there was no stop. Yeah, so it has a huge application there. But then if we look more in depth, these are the various applications. Like I said before, transportation. I don't know if all of you have heard of the maglev trains. They are the magnetic levitation trains. They move almost at the speed of about 513 kilometers per hour, as against the normal conventional trains that move about 300 to 50 thereabouts. Yeah. So that makes them really cool. The second one I also read recently about was about the electric ships. Yeah, like you see in normal conventional ships, they are huge with all the cables and all that stuff. So if you can get superconducting wires, the fact that they are light and they can contain as much current as possible, meaning high current density, ships can be more economical and they can even have more space, like for room on board and all that stuff. So that's definitely one area guys in the industry have been looking into, and how they can make superconductivity very effective in the transportation industry. The second one is medical imaging and diagnostics. For MRIs and NMRs, that's magnetic resonance imaging and the nuclear magnetic resonance spectrometer. Like they usually require a very strong field for them to function. Like you want to get the inner structures, the extreme details of things. You would need an extremely strong magnetic field. And for normal conventional, that the conventional magnets you have today, they are not, like they are effective, but they are not as stable. For example, they can't sustain that magnetic field for the period superconducting magnets can. So that's also one aspect that superconducting magnets have proved very futile. The third one is high particle physics. The Large Hadron Collider, something that what they call them, all these cosmologists, astronomers, and all that stuff have been looking into. They are trying to kind of fathom what happened like seconds before the world was created and all that stuff. So like you need these particle accelerators to make sure the electrons are moving at the fastest speed that you can ever imagine. And that's also one place that superconducting magnets have proved very effective. And the last one, like Mehdi was talking about in his last presentation, quantum computing. You talk about trying to sustain the whole 0-1 thing. The bits and the bytes, like there's something they call it decay. I don't know much about the dynamics of it, but then superconducting magnets are also used in quantum computers. And there are other applications as well. Still in medicine, for example, you talk about the magnetospectrometer, something along those lines, like just anything that might need an extremely strong field for it to function. Superconducting magnets have been very good at doing that. And so what next? I didn't talk about that before, but then a few years after these guys discovered low temperature superconductors, they also discovered high temperature superconductors. And I know many of you might be looking high temperature. What do I really mean by high temperature? The high temperature they're talking about here is something like 38 Kelvin, 100 Kelvin, so it's still low temperature, all the same. But the disparity between the fact that when they first discovered superconductors, they were existing like 4 Kelvin, 5 Kelvin, 6 Kelvin. They wanted to differentiate between both conductors. And about high temperature superconductors, like I explained before, the BCS theory was able to explain why superconductors were so. But then when they discovered high temperature superconductors, it's faltered in a lot of ways, like from what the BCS theory had predicted. So many people try to think of the theoretical view as to why high temperature superconductors existed until today. they've not really come out with something congent, because there was this thing about the S wave and the D wave, and they are finding them to function in both low temperatures and high temperatures. So they've not really drawn the distinct and unique properties of high temperatures and low temperature superconductor. That's definitely an area professors are still looking into. Also, like I said before, it's going away from the leap from normal superconductivity in the fact that the properties are different, the conditions are different, and all that. And lastly, I'd just like to end by trying to draw the parallel between superfluidity and superconductivity. Everyone knows superconductivity occurs in metals, but then recently, okay, not recently, it happened as early as 1970s. But then people are beginning to notice liquids that can also lose their resistance at extremely low temperatures. Liquids like helium, for example. Yeah, so this could be a major focus area for people in the field of what do you call it, gases and all that. Like, since we've been able to discover metals that can function at low temperatures, lose their resistance, probably we can start looking into things like water. Who knows? Maybe something might come out of it. Yeah, so that's pretty much everything about superconductivity. Any questions?
So Daniel, when you talk about the lightweight of the wires that are necessary, you could have our mains power that we get from the power utility running on really, really thin wires that you ordinarily wouldn't use for high voltage, is that right?
Yeah. Like, one thing about them is that the fact that you can have an extremely, like the normal conventional wire, but carrying as much current as possible is what makes them really cool. So you can have thin wires, you can have big wires, but the fact that they can contain more current is more or less the density itself, and not necessarily the shape of the wire.
Yeah, so is it all metals that are super conductive, like if you change the environment, or some of them?
Maybe most metals are, like all of them have their different temperatures where they all lose their resistance. But for what I've read so far, most metals are super conductive.
Okay, so how do they do to control the temperature in computers and things like that? How do they do?
Yeah, so maybe I didn't say that before, but the applications I talked about, most of them, not all, some of them are already being used, but most of them are things that are being looked into. And so one of the things we basically need for that to function is an extremely low temperature. So you require helium for cooling and all that stuff, and helium is expensive to get. So that's one of the things that's created an itch for them to advance in such research. But then, yeah, it can happen if you can achieve things like room temperature superconductivity.
I have a quick question. So, in a regular circuit, you hook up a power supply and you get current because there's resistance. But in this one, if there's no resistance, how do you keep it going without a power supply? Like, how do you physically get the power supply out of there so the current keeps on going forever? I guess it doesn't need a power supply, right?
Okay, can you rephrase your question again for sure I understand?
Well, I'm thinking of Ohm's law.
Okay.
If R is 0, then the voltage that you need to get the current going is 0, right? So you don't need a power supply there.
I think if that actually happens, like, so many things will change in physics, like probably some of the laws that have been in play for so long. I think you might still need a power supply because you need an external thing to inject the current out before.
But just to start it, right?
Yeah, to start it, yeah.
And then you just let it go. That's
Yeah.
crazy.
Yeah, it's crazy, but yeah.
Huh. Interesting.
Any other questions?
Thank you so much, David.
You're welcome.